The floor of Yellowstone is falling. It does not sink smoothly or all at once, but in jolts several feet at a time, as an enormous block of crust gives way beneath the center of the park, with each sudden drop registering as an earthquake, while in the intervals between them, the ground continues to tremble in one long, unbroken signal, the sound of fluid forcing its way through rock that is beginning to fail. What is sinking is not a crater in the familiar sense, because there is no mountain with a summit here and no single mouth opening at its peak. Yellowstone's caldera is roughly 45 by 80 kilometers, about 28 by 50 miles, so wide that you can drive across it without realizing you have entered a volcano, and now fractures are opening around parts of its buried rim, releasing a wall of ash and gas that rises rapidly into the atmosphere. The scene is imagined, but the physics is not, because if Yellowstone's least likely eruption began tomorrow, this is one way its opening hours could unfold. The eruption column would climb with extraordinary speed, possibly reaching 30 to 50 kilometers, 20 to 30 miles above the ground, 4 or 5 times the cruising altitude of a passenger jet. And when it could rise no farther, it would begin spreading outward, flattening against the upper atmosphere until it formed an umbrella cloud hundreds of miles across. Inside that cloud, billions of particles would collide and separate, building electrical charge until lightning began flashing through the ash, and thunder rolled through a sky already darkening over Wyoming, Montana, and Idaho as the eruption generated a weather system of its own above the northern Rocky Mountains. Not everything leaving the vents would remain in the sky, however, because as the eruption intensified and the column became too dense to support its own weight, parts of it could collapse back toward the ground and spread outward as pyroclastic density currents, avalanches of ash, pumice, shattered rock, and superheated gas that behave less like ordinary wind than like a flood stripped of water's patience. These currents are not lava, which usually moves slowly enough to be watched and avoided. They can travel faster than highway traffic, cross valleys in minutes, and climb over ridges that would divert an ordinary flood, carrying enough heat that when their ash finally settles, it can fuse back into solid rock. Much of Yellowstone's plateau is made from precisely that kind of rock, the hardened body of an earlier eruption still lying where it came to rest. Beyond the reach of those currents, ash would begin falling across the northern Rocky Mountains, filling the air like heavy snow but refusing to melt when it touched the ground. Volcanic ash is not the soft residue left after a fire, but a mixture of jagged glass, crystals, and fragments of older rock, much of it fine enough to breathe and abrasive enough to damage anything with moving parts. Fresh and dry, a cubic meter can weigh between 500 and 1,500 kilograms, roughly 1,100 to 3,300 pounds, and if rain soaked into it, that weight could nearly double. Near Yellowstone, the fall could become deep enough to bury roads, overload roofs, foul water supplies, and turn daylight into a dim grey afternoon. While farther away, the layer would grow thinner without becoming harmless, because even a few millimeters can close airports, erase road markings, contaminate machinery, and disrupt electrical systems across regions that never heard the eruption itself. Nor would the ash travel in a simple trail downwind. At this scale, the umbrella cloud would spread partly under its own power, pushing ash north and south, and even back against the prevailing wind, so that while the deepest deposits remained near Yellowstone, a fine grey layer could eventually reach every coast of the continental United States, the devastation near the vents arriving with extraordinary violence, and the disruption thousands of miles away settling almost silently from the sky. All the while, beneath the column and the spreading cloud, the caldera floor would continue to descend, not because the eruption had left an empty underground cavern behind, but because magma and gas were escaping from the reservoir faster than the system could replace them, reducing the pressure and mechanical support beneath the crust until the enormous block above began slipping along curved faults around the caldera. The collapse would not happen in one clean motion because the roof block could remain suspended for a time as friction held it in place, only to fall suddenly when that resistance failed, and each downward step could squeeze the reservoir beneath it like a piston, forcing another surge of material from the vents so that collapse fed the eruption even as the eruption drove the collapse. By the time the process ended, hundreds of cubic kilometers of magma and broken rock might have left the system. Much of the park could have been transformed into a smoking plain, and the caldera floor might stand hundreds of meters lower than it had before, leaving behind a scene that sounds as though it belongs to a disaster film, even though the ground beneath Yellowstone preserves evidence that it has happened before. During the past 2.1 million years, the Yellowstone volcanic system has produced 3 enormous caldera-forming eruptions, and when the most recent of them occurred about 631,000 years ago, the floor fell by hundreds of meters and left, along one edge of the collapse, a wall roughly 500 meters high that still stands beneath the forest today. Over the ages that followed, thick lava flows filled much of the depression. A lake settled into part of what remained, and forests spread across the cooled rock until roads could cross the crater without revealing what lay beneath them, leaving Yellowstone with a caldera so broad and so gentle in appearance that millions of people now enter it every year without ever seeing a rim. The eruption we have imagined is not a prediction. Nothing being measured at Yellowstone today suggests that a volcanic eruption, large or small, is approaching. The volcano remains at its normal background level of activity, and the magma beneath it is mostly locked inside a framework of hot crystal. But the record of what Yellowstone can do is real. It survives in welded cliffs inside the park, in ash beds thousands of miles away, and in a caldera so large that people stood inside it for generations before geologists understood what it was. So the question is not whether the Earth is capable of such a day. It has already had that day. The real questions are how it happened, what the next Yellowstone eruption would most likely be, how much warning we would receive, and what this ancient volcano is actually doing beneath the park tonight. This is where we're going. We'll begin with the evidence Yellowstone has already left behind, its buried calderas, its continent-wide ash beds, its rising and falling ground, and the mostly solid magma reservoir beneath the park tonight. We'll separate the eruptions that are genuinely possible from the one that has come to dominate every headline, and ask what the next Yellowstone eruption would most likely be. Then, once the record is in place, we'll return to the day we imagined at the beginning. We'll follow the least likely and most destructive scenario from its first warning signs to the opening of the vents, from the collapse of the caldera to the spread of ash across the continent. We'll move through the first hours, the first week, the first growing season, and the years of recovery that might follow. And at every stage, we'll distinguish what the evidence tells us would happen, what scientific models suggest could happen, and what remains too uncertain for anyone to predict. This is not a forecast. It is a scientific thought experiment, built from the eruptions Yellowstone has already produced and from disasters that modern instruments have actually recorded. But before we step into Yellowstone's past, if you're fascinated by deep time and the forces still shaping the world beneath us, consider subscribing to continue these journeys through Earth's history. And let me know in the comments where you're listening from, your city and your time zone. There is something remarkable about people scattered across the modern world, all awake at different hours, listening together to the story of a volcano whose history is measured not in generations, but in millions of years. Now, let's begin. But the story of Yellowstone does not begin inside the park. It begins 900 miles away on the plains of Nebraska, in a rain-cut ravine where a bed of grey volcanic ash has been lying for 12 million years, with the animals it killed still inside it. In the summer of 1971, a paleontologist named Mike Voorhuis noticed something looking out of the wall of that ravine. A storm had taken a slice off the bank, and high on the fresh face there was a band of grey volcanic ash, pale against the soil. Working its way out of the ash was a skull, the skull and lower jaw of a rhinoceros, small enough to be a calf, and whole. Voorhuis worked for the State Museum, and what he had in front of him was, by the standards of his trade, a good find and nothing more. One animal in a layer of ash that had clearly fallen a long time ago. It took until the end of that decade and money from the National Geographic Society to open the bed properly, and what came up out of the ground was a herd. More than 200 skeletons have been lifted or uncovered so far, and more than 100 of them are rhinoceroses, the heavy, barrel-bodied kind, lying where they went down, calves among the adults, three-toed horses and camels and birds around them. The ash had filled a waterhole. The animals had come to it and stayed and died there slowly over weeks, and what killed them was not burial but breathing. Today a roof stands over the bed. The bones are left in the ground exactly where they lie, and you can walk in under the roof and stand a few feet from them. Two things about that ash matter more than the animals, and the first is how much of it there is. Away from the waterhole, the same bed runs about a foot deep across 250 miles of Nebraska. It is a foot deep under the grass you would be standing on, and a foot deep under the next farm, and under the one after that. The hollow where the herd died holds 8 to 10 feet of it only because the wind drifted it there, the way snow drifts into a ditch and lies shallow on the field beside it. The second thing is where it came from. Look west from that plain, and there is nothing to see, not in the whole of the view, and not for 900 miles beyond it. The volcano that did this stood in the far southwest corner of what is now Idaho, 12 million years ago, and it is not there anymore. That is an odd sentence to write about a volcano because volcanoes do not leave. Mountains that erupt are mountains still, long after they go cold. This one, though, has no mountain, and its crater is buried, and to understand why you have to stop looking at Idaho as a place and start looking at it as a conveyor belt. When Ken Pierce and Lisa Morgan set the whole thing out in a long paper in 1992, they were describing a pattern that had been noticed in pieces for decades. Starting near the point where Oregon, Nevada, and Idaho meet, around 16 million years ago, a series of enormous calderas runs across the map, each one younger than the one before, and each one farther to the northeast. The field that buried Nebraska formed at about 12 million years. Others came at roughly 10 and 6 and 4. And then, about 2 million years ago, the heat arrived under the ground that is now the park. The line is the best part of 700 kilometers long. Nearly all of it lies under the Snake River Plain, which is to say under younger lava, and then under soil, and then under farms, so that the largest volcanic craters on the continent are places where people grow crops and do not think about it. On the map, it looks like a volcano that walked. The truth runs the other way. The heat stays put. It is the continent that moves, sliding to the southwest over the source at a few centimeters a year, somewhere between 2 and 4, depending on how the measurement is made. And so the hole the heat burns through the crust is carried off to the northeast and buried, and a new hole is burned behind it. Over a human lifetime, the continent travels across that fire by about the length of a bed or of a small car. Over 16 million years, it has traveled the length of Idaho. Pierce and Morgan counted the big eruptions along the line and found a rhythm in them, and for a while, that rhythm was the rhythm. Then, in 2020, a team working in the middle of the plain went back through deposits that had been mapped as many small events and found that 2 of them were not small at all. They were 2 more super eruptions, both roughly 9 million years old, and one of them, at a place called Gray's Landing, was larger than anything Yellowstone itself has ever produced. With those 2 counted, the rhythm changed shape. Along the older part of the line, the heat had managed a super eruption about every 500,000 years. Along the younger part, it managed one about every 1.5 million. That is 3 times slower, and the word the authors used for it was waning. Their explanation was that the continent is now carrying older, thicker, colder crust over the fire, the kind of crust that is harder to melt, and that the heat may be losing its argument with the rock. What the heat actually is down there is still being argued about, and honestly so. In 2018, a group using earthquake waves that had passed right through the planet drew a slow, hot column some 350 kilometers across, rising from the boundary between the core and the mantle, leaning as it came and arriving under the park. In the spring of 2026, another group, writing in the journal Science, argued almost the opposite, that the melting is driven from much shallower down by the stresses inside the plate itself, with what they called a negligible contribution from any plume. Both groups have the same line of craters to explain. We do not yet know which of them is right, and it may be some years before anyone does. What is not in doubt is the line itself and the direction it runs, and the fact that the ground under the park is simply the most recent place on it. It helps to hold the whole thing at once. A fire that has stayed roughly where it was for 16 million years. A continent sliding over it, a bed's length a lifetime. A hole burned, carried away, buried under lava, and then under wheat. Another hole burned. A waterhole in Nebraska where a herd lay down in a foot of glass that had come 900 miles on the wind. And the line ending, for now, under a high plateau in the corner of Wyoming, where the crust slid into place over the heat about 2 million years ago, and the first thing the fire did to it is written in rock along the park's edges, in a layer that did not go down all at once. Ash came first, and as far as the layers can be read, it kept coming for weeks before anything worse happened. That is the bottom of the record, a bed of fallen ash, settling out of a column that rose and thinned and rose again over ground that was not yet a plateau, while whatever lay beneath it gathered itself. Then the roof gave way, and the eruption that followed is the one the park's geologists still measure everything else against. It is called the Huckleberry Ridge Tuff, after a ridge in the south of the park where the rock stands exposed, and tuff is the plain word for ash that settled hot enough to weld itself back into stone. The numbers attached to it are these. Something like 2,450 cubic kilometers of material came out of the ground. The hot currents that carried most of it buried about 15,500 square kilometers of country, and the hole left when the roof came down was roughly 90 kilometers long and 50 wide, much of it lying west of today's park boundary, in Idaho, under the flat country called Island Park. 2,500 cubic kilometers is a figure the mind slides off, so it helps to give it a body. All the water the Mississippi carries past New Orleans into the Gulf of Mexico in a year comes to a little under 600 cubic kilometers. The first Yellowstone eruption was about 4 years of that river, and it was rock. Nobody measured it, of course. It is reconstructed, and the way it is reconstructed is worth knowing, because every number in this story comes from the same kind of patient work. The sheet of welded ash outside the crater can be mapped, where it lies, how thick it is, where it thins to nothing. Multiply the area by the thickness and you have the outflow. Inside the crater the fill is harder because most of it is buried under everything that came later, and it has to be worked out from drill holes and from the few places where erosion has cut into it. Add the two together, add the ash that fell far away as a dusting rather than a sheet, and the total is an estimate with honest uncertainty in it. Its age has uncertainty of its own. One laboratory's method puts the eruption at about 2.08 million years ago. Another's, using a slightly different calibration of the same radioactive clock, puts it at 2.13. 50,000 years separate two good answers. Both teams know it, and the United States Geological Survey writes about 2.1 million and gets on with the mapping. What the rock says most clearly, though, is neither a size nor a date, but a shape in time, and it is the shape that should stay with us. The tuff comes in three layers, called A, B, and C, and the joins between them carry the marks of time passing. Between the first and the second, there are signs of weeks, perhaps months. Between the second and the third, in one careful reading, there were years to decades, and in the most recent dating work, the third came as much as 20,000 years after the other two. So the first eruption lasted a great deal longer than a day. It started and stopped, and the ground went quiet long enough for anyone, had there been anyone, to believe it was over. Then it started again, and once it may have waited long enough for whole forests to grow on the ash before it finished. 800,000 years then passed before the ground did it again, and that number deserves a moment of its own. Our species has existed for something like 300,000 years. The quiet between the first Yellowstone eruption and the second was more than twice as long as everything we have ever been. The second eruption is called Mesa Falls, for the waterfall on Henry's Fork of the Snake River where its rock stands in the cliffs, and by the standard of the first it was small. 280 cubic kilometers, about a tenth, a crater some 20 kilometers across rather than 90. And by the threshold the survey uses, which is 1,000 cubic kilometers, not a super eruption at all. That is the honest word for it, and it still describes an event larger than Tambora in 1815, the biggest eruption in the whole of written history, the one that took the following summer away from Europe and New England. Small here is a relative term, and the relation is the point. The same fire under the same stretch of crust, 800,000 years apart, produced one eruption 10 times the size of the other. There is no standard Yellowstone eruption. There are only the ones that happened, and they do not match. A claim gets made about the first of them so often that it deserves a fair hearing, that Huckleberry Ridge was the largest volcanic eruption the Earth has ever seen. You can see why it caught on. 2,500 cubic kilometers sits beyond the reach of ordinary comparison, and for a long time the catalogues of such things were thin. They are not thin now. A tuff in southern Colorado, the Fish Canyon, came out of the ground 28 million years ago at more than 5,000 cubic kilometers. Toba in Sumatra, 74,000 years ago, is put at 2,800 cubic kilometers of magma, and a good deal more as fallen ash. And on Yellowstone's own line, back down the Snake River plain, the crater at Gray's Landing was bigger than this one. The first Yellowstone eruption was enormous. It was not the largest, and it does not need to be. What both eruptions left far from the crater is what lets anyone date and size them at all, and it is also the part of them a person can still touch. The ash went everywhere. The bed from the first eruption has been matched across some 3,000 kilometers, from cores drilled into the seabed off Northern California to the plains. And when Glenn Isett and Ray Wilcox of the survey drew up the map of it in 1982, they had about 300 places where one Yellowstone ash or another had been found: California, Texas, Iowa, Saskatchewan. In a dry lake bed in the Mojave at Tecopa, it lies thick enough to quarry. And on the high plains of Kansas, north of the town of Meade, the beds were known to farmers long before anyone knew where they were from, as bands of silver grey in the creek banks, and a local post office gave them the name Perlette. Wilcox and Izett went to Meade in the 1960s and found that the Perlet ash was not a single ash, but at least three, one above another, with the whole Yellowstone sequence lying in them. Kansas has mined that ash for decades, 2 million tons of it out of more than 35 pits, sold as abrasive, as an additive for cement, as a dressing for roads. So it is possible, on an ordinary afternoon in Kansas, to pull over beside a road cut and pick a pinch of Yellowstone out of the bank. Rub it between your finger and thumb, and it is gritty because every grain of it is a shard of glass. Which of the eruptions it fell from you cannot tell by eye. The beds look alike, and it took a laboratory in the end to tell them apart. The band in the cut is a hand's width thick and the color of old silver, and 3 fires lie in that wall, one above another. The topmost is the youngest of the 3, and it is the one that left a crater still open to the sky. Stand on the road that runs through the middle of the park, somewhere along the loop the visitors drive, and look for the youngest of the 3 craters. You will not find it. For most of a century nobody did. Not the painters, not the map makers, not the geologists who named the geysers one by one and worked out how they were plumbed. People came in their millions and stood inside the thing without seeing it because it was too large to take in from the ground. A crater, to the eye and to the ear, is a bowl you can stand on the edge of and look down into. This one is roughly 45 kilometers across and 80 long. Its rim, where it survives at all, is a low rise in the forest you would drive over without a second glance. Drive the whole loop all the way round, and something like a third of it lies inside the crater. There is no cone. There is no summit to climb. The floor of it is most of the park. The man who first understood what he was looking at was a graduate student from Harvard named Joe Boyd, working on the plateau in the 1950s. The pale rock across great stretches of the park had long been called rhyolite and taken for old lava, cooled from flows that had oozed out and set. Boyd looked harder and saw that much of it was nothing of the kind. It was welded tough, ash that had come down so hot and so thick that it fused into stone where it settled. The loose grey grit that reached Kansas had, here at its source, fallen as a red-hot blanket and set as hard as the cliffs. Ash welded on that scale does not come from a lava flow. It comes from an eruption that throws out rock by the cubic kilometre and lets it settle glowing, and an eruption like that leaves a hole behind it. When Boyd published in 1961, the hole he pointed to was the first line of the map. The mapping itself fell to a team from the United States Geological Survey, and its central figure was a geologist named Bob Christiansen, who would give the better part of his life to this ground. They began in the middle of the 1960s, and some of the money came from an unexpected quarter, the space agency, NASA, which was learning to photograph the Earth from orbit and wanted patches of well-mapped country to test its images against. The story is sometimes told that the caldera was first caught in one of those photographs, a vast ring seen all at once from above. It is a tidy story, and it is not quite what happened. The ring came out of 6 summers on foot, 3 months a year of walking and hammering and following one ash layer into the next, and by the time Christiansen and his colleague Robert Blank set it all down on paper in 1972, the plateau held not one buried crater, but 3, from 3 eruptions strung out through time. The youngest of them is called the Lava Creek eruption, and it happened about 631,000 years ago. Roughly 1,000 cubic kilometers of material came out of the ground. The ash flows spread across more than 7,500 square kilometers, and the roof, emptied from beneath, came down. The surface subsided by many hundreds of meters, and along one edge, the collapse left a wall 500 meters high. That wall is still there, grown over with forest now. If you walk to its foot and look up, you are looking at the depth the floor fell. Like the first eruption, it was not a single stroke. It came from two overlapping rings of fractures rather than one mouth, and the ash records at least two main pulses with a pause between them, long enough for the first sheet to cool and begin to weather before the second buried it. There is also a clock of a subtler kind hidden in the crystals. Read the feldspar grains closely, rim against core, and they show that the magma was reheated, nudged back toward eruption over a span of decades before it finally broke out. Not centuries and not an afternoon. Decades. That detail will matter a great deal later when the question becomes how much warning the ground might give. The ash from it traveled the way the older ashes had. The lava creek bed has been matched across some 2,400 kilometers. It lies a full meter thick in New Mexico in a formation called the Gatuna. It shows up in old seafloor sediments raised along the California coast. And in cores drilled from the bottom of the Gulf of Mexico, it reaches tens of meters deep. Not because that much fell there, but because rivers, the Mississippi chief among them, spent the ages afterward washing loose ash off the continent and carrying it down into the deep. So now there are 3 dates, and it is worth setting them side by side, because the moment you do, a familiar idea comes apart in your hands. The first eruption, about 2.1 million years ago. The second, about 1.3 million. The third, about 630,000. The gap between the first and the second was around 800,000 years. The gap between the second and the third, around 660,000. Those two numbers are not the same, and 3 eruptions give you only those 2 gaps, 2 unequal intervals, which is not a rhythm and cannot be made into a clock. Yet a clock gets built from them all the time. The claim is everywhere that Yellowstone erupts every 600,000 years or so and is therefore due and perhaps overdue. The dates will not carry it. Take the rough average of the 2 gaps, about 730,000 years, measure forward from the last eruption, and the park has not yet reached even that average. By the survey's own reckoning, it is something like 90,000 years short of the point where the word overdue could honestly be spoken. 90,000 years is longer than our kind has lived anywhere outside Africa. The arithmetic quiets one fear and leaves a better question standing in its place. About 25,000 human generations have passed since the floor last dropped, and in all that time the crater has done nothing but fill and soften and grow its forest until it became a place too gentle and too wide to read as a crater at all, which is perhaps the honest answer to whether it deserves the word. But an interval is only a number on a page. It records how the past was spaced. It says nothing at all about whether the thing that made those eruptions is still assembled and warm beneath the plateau, or cold and finished. That is not something arithmetic can reach. Learning it means going out, putting instruments on the ground, and listening to what it is doing now. There is a thermometer for the whole plateau, and it is the rivers that leave it. Hot water underground picks up chloride from the rock, and every spring, every geyser, every unnamed seep eventually leaks its share into the streams. So you can stand at the gauging stations on the rivers flowing out of the park, measure the chloride going past, and work backwards to the total amount of hot water the ground is giving up. It comes to somewhere between 3,000 and 4,000 litres every second. Keeping that much water hot takes between 4.5 and 6 gigawatts, held steady year-round, the continuous output of several large power stations running day and night, with the ground itself as the furnace. Averaged across the caldera, the heat coming up through the surface runs about 30 times what an ordinary piece of continent manages. In the thermal basins, it is another matter entirely. There, the ground can push out more than 100 watts through every square meter, the heat of a bright, old-fashioned bulb burning under each pace you take, which is why the boardwalks steam on frosty mornings and the snow refuses to lie. The ground breathes gas as well as heat. Carbon dioxide seeps out of the soil of the park at a measured rate of around 45,000 tons a day, from a volcano whose last eruption ended tens of thousands of years ago. And it holds more than 10,000 hydrothermal features, among them upwards of 500 geysers, more than half of all the geysers known on Earth, in one high crater. The tallest of them anywhere, Steamboat, throws water 300 to 400 feet into the air when it chooses to, and in 2018 it woke from decades of near silence and began erupting again and again. The scientists who went looking for the reason found no new magma, no heating of the underground reservoir. Nothing changed but the geyser's own habits. The plumbing, they concluded, keeps a private schedule. None of this heat is left over from the Great Eruption. 600,000 years is far too long for that. It is being delivered still from below, and the lavas are the proof of what the delivery could once do. After the floor came down, the crater refilled the hard way, not in one flood but in dozens of separate eruptions of thick, slow rhyolite, and the biggest of them came late, in a handful of pulses between about 170 and 70,000 years ago, more than 600 cubic kilometers of lava in all. The broad, level plateaus the road crosses are the tops of those flows. The youngest, called the Pitchstone Plateau, went quiet around 70,000 years ago, and nothing has erupted here since. The oldest human footprints anywhere in the Americas, pressed into lake mud at White Sands in New Mexico, are about 21 to 23,000 years old. The youngest Yellowstone lava is 3 times their age. No human being anywhere has ever seen this volcano erupt. The geologist who has worked most closely on those lavas, Mark Stelton of the survey, reads the reservoir beneath the park today as the mostly solidified remnant of the batch that fed them, a system that seems to alternate over its long life between cold, crystalline centuries of thousands and shorter ages in which it holds magma fit to erupt. Which age we are in is a question the lavas alone cannot answer, but the heat, the gas and the geysers say the furnace below has not gone out, and that makes the twitching of the ground feel ominous to us in a way it rarely deserves. The clearest lesson on that point was delivered on a single summer night, and it had nothing to do with magma at all. At 11:37 in the evening on the 17th of August, 1959, a fault let go just beyond the park's western edge near Hebgen Lake in Montana, with a magnitude of 7.3. South of the lake, the wall of the Madison River Canyon came down, some 50 million cubic yards of mountainside in less than a minute, and it came down on a summer campground. 28 people died that night, most of them there, asleep beside the river when the slope above them failed. The rock dammed the Madison Hole, and behind the dam a new lake began to rise in the dark. It is on the maps now as Earthquake Lake, and the drowned trunks still stand in it. The ground surface itself tore in fresh scarps up to 20 feet high, running for miles. Hebgen Lake tilted in its basin, and the water rocked from end to end for hours, riding over the top of the dam again and again. The dam, remarkably enough, held. And inside the park, the plumbing convulsed. In the geyser basins along the Firehole River, at least 289 springs boiled up as geysers in the hours and days after the shock. Someone went out and counted, and 160 of them had no record of ever having erupted before. Hundreds more turned grey and turbid as the shaking stirred a century of silt. Sapphire Pool, which had been a modest thing, puffing a few feet high every 20 minutes or so, spent the next 9 years as one of the great geysers of the world, hurling bursts 150 feet high and 200 feet across before it finally subsided. Even Old Faithful changed. Its average interval that summer had been the shortest on record, a little under 62 minutes. By December, it was running past 67, and the drift it began that year has never fully reversed. One earthquake, from a fault that belongs to the stretching of the Rockies rather than to the volcano, reset instruments across an entire hydrothermal system in a night. And for all that violence, with the basins in uproar and new geysers by the dozen, no magma moved. The furnace was rattled, hard, and it did nothing. What the volcano does on its own when nothing rattles it is slower and stranger. It breathes. Surveyors ran a line of elevation benchmarks across the park in 1923, along the roads, and half a century later, a team from the University of Utah thought to run the line again. The road across the middle of the caldera had risen by more than 70 centimeters, about 14 millimeters a year every year for 50 years, and when the result was published in Science in 1979, it changed what this place was understood to be. The lake had been saying the same thing all along to anyone who looked. The caldera floor lifts near the lake's northern end, tilting the whole basin southward so the water creeps up the southern shores, and stands of lodgepole pine along the southern arms have drowned where they grew. Since then, the breathing has been watched continuously. Through the middle of the 2000s, the floor rose at up to 7 centimeters a year for a few years, driven, the modeling suggests, by fresh, molten rock spreading sideways 10 kilometers down. Then it slowed and stopped and settled back. More recently, a patch of ground on the caldera's north rim lifted about 1.5 centimeters over half a year, and then that stopped too. A century of records now, uplift and subsidence, swarm and quiet, and every single episode has ended the same way, without an eruption. Centimeters up and down, across a human century. That is this volcano at rest, and it is the state every instrument in the park is reading tonight. Between centimeters in a century and a floor falling by hundreds of meters in a week, there is an enormous distance, and everything still to come here lives inside it. When the next eruption comes to this ground, and on ground this alive one day one will, what will it actually be? The question sounds like it has one answer, the enormous one, because that is the only Yellowstone eruption anyone ever talks about. The record talks differently. It offers 3 futures, ranked, with gulfs of likelihood between them, and the way back into the day this all began with is to take the rungs of that ladder in order, starting from the one the ground steps onto most often. Begin with ice, oddly enough. 18 or 20,000 years ago, in the last deep cold, the plateau carried a cap of ice more than 1 kilometer thick. Stand anywhere in the middle of the park then, and there would have been 1 kilometer of it above you. One lobe of a frozen system that covered some 20,000 square kilometers of high country. Around 15,000 years ago, it let go, and in the few thousand years after the weight came off, the hydrothermal system threw the biggest tantrums in its record. The floor of the park is dimpled with round craters from those centuries. The largest of them is now a bay. Mary Bay, on the northern shore of Yellowstone Lake, is 2.5 kilometers across, about 13,000 years old, and it is the largest hydrothermal explosion crater known anywhere on Earth. Hydrothermal is the operative word, and it means the magma stayed home. Under the basins, water sits in the rock far hotter than the boiling point, kept liquid only by the pressure of everything above it. Take some of that pressure away. A departing ice sheet, a falling lake, a hard earthquake, sometimes nothing anyone can identify, and a column of it flashes to steam all at once, swelling to more than 1,000 times its volume in a moment that excavates the ground above like a quarry blast. No lava is involved, and none follows. It is the plumbing, not the furnace, and the whole affair lives closer to your boots than to any magma. One reconstruction of Mary Bay blames a large earthquake and a sudden drop in the lake level, working together on water that needed only an excuse. Steam explosions are, by a wide margin, the most likely next eruption at Yellowstone, and the survey has read their rough tempo out of the craters they leave. The small ones, a meter or two across, happen somewhere in the park every year or so. Something the size of the blast that wrecked Porkchop Geyser in 1989 comes along every few years. The size that makes national news, perhaps once a decade or a few times a century. Craters of an acre, once in several hundred years. The giants of 10 acres and more, once in several thousand. Say, on average, after every one of those figures, out loud, because they are numbers read backwards out of holes in the ground, they are good to about a power of 10, and the process behind them keeps no calendar. The truthful unit for the newsworthy ones is roughly once in a lifetime, give or take a lifetime. What that looks like, close up, we now know exactly, because it has just happened twice in the same corner of one basin, though not the second time from the same mouth. On the 23rd of July, 2024, a few minutes before 10 in the morning, Black Diamond Pool in Biscuit Basin, a short drive up the road from Old Faithful, detonated without any warning at all. A column of steam, mud and grey rock stood up out of the pool to somewhere between 120 and 180 meters, the height of a 40-story building, and dropped boulders the better part of a meter across onto the boardwalk, which did not survive. Dozens of visitors were standing there filming when it went. Not one of them was hurt, which the rangers will tell you was luck as much as anything. And when the seismologists went back through the records afterwards, they found nothing. No swarm, no rising note in the ground, no precursor their instruments could see. The pool simply went. The basin was closed after that, and in the following summer the observatory put a monitoring station 100 meters from the pool, closer to it than the far end of the old boardwalk would have put you. It was a well-placed bet, though not in the way anyone expected. Just after 5 in the morning on the 13th of June, 2026, the instruments caught it, seismic energy, and beneath it the deep pressure below hearing that seismologists call infrasound. When the geologists got there, the pool itself was innocent. Its temperature trace showed only a small blip, nothing like the sharp drop that follows a real eruption of black diamond. The ground had opened instead, 100 meters or so to the north, along 3 separate groups of vents that had not existed the day before. It was still the first hydrothermal explosion anywhere recorded at close range. The station had been aimed at the wrong feature and caught the right one. The largest of the new openings was a fissure 18.5 meters long, with water standing at 90 degrees in it. Within a few days, a collapse nearby had become a new pool, roughly 6 meters by 5, which spent that week spouting boiling water 2 and 3 stories high. The park, in other words, gained a named feature it had not possessed a month earlier, and no magma came anywhere near it. This is the ordinary volcanism of Yellowstone in our era, violent, local, strange, and finished in a morning. One rung up sits lava. The crater floor is paved with the stuff, laid down in dozens of separate eruptions in the 600,000 years since the collapse, and there is no reason to think that story is over just because the last flow cooled 70,000 years ago. If a vent opened here, nothing would race anywhere. The rhyolite is too stiff for that. It would grind outward and pile up in cliffs, the way it built the plateaus, burying whatever ground it crossed and burning what it touched. For anything inside the park, that is a grave event. For the continent, it is barely weather. The survey's ranking is blunt on the order. Steam explosions first, lava flows second, both of them overwhelmingly more probable than the third thing. The third thing is the caldera event, the emptied chamber, the falling floor. On the ladder of likelihoods, it stands at the bottom, the least probable eruption this ground can produce, the one the arithmetic of the 3 dates cannot even schedule. When the survey and its partners wrote the formal hazard assessment for the region, they worked through the whole spectrum. Depending on the season, they found 70,000 to more than 100,000 people could be affected by the more violent possibilities in and around the park. And the most violent of all would reach beyond any region, out across the continent. Then they filed it correctly under remote. So there is real relief in the ladder. The overwhelmingly probable futures of this volcano are a morning's boiling water and, someday, a slow wall of lava inside a national park. But the question we set out with was never about what is probable. It began with what if, and a what if walks past the safe rungs on purpose, down to the bottom one, and stands on it. From here on, that is where we stand. The day from the beginning, the column, the currents, the falling floor, gets taken at its word now and followed through, hour by hour and season by season, built from measured eruptions and from this ground's own record. The grammar carries the honesty, would for what physics compels, could for what depends on wind and luck, might for the far dim edges. And the moment you stand on that rung, the first question is not about the eruption at all. Between the centimeters of the breathing caldera and a chamber ready to empty, something enormous would have to change beneath the park, and it would have to change first. If the least likely thing on the ladder were truly coming, how much warning would this ground give? The crystals answer part of it before the instruments say a word. A feldspar grain growing in a magma chamber lays down its substance in layers, like a very slow pearl, and when a charge of fresh, hotter melt arrives from below, the grain records it, a rim with a different chemistry, a thin, bright line of changed conditions. Because atoms keep diffusing through the crystal at temperatures like these, at rates that can be measured in a laboratory, the sharpness of that line is itself a clock. Blur it a little and months have passed. Blur it more, years. Read this way, one of the lava flows that refilled the crater says that new magma pushed into its chamber, and the eruption followed within about 10 months. Other grains from the same family of flows say 10 years. And the ash of the Great Lava Creek eruption, as we saw, carries in its feldspar the record of decades of reheating before the end. Months, years, decades. The volcano does clear its throat before it speaks. What the crystals cannot tell us is when the throat clearing would first become audible at the surface, because they are read after the fact from rock that has already erupted. For the view from above, while it is happening, we have to rely on the machines. The machines are these. Around 46 seismometers stand watch over the plateau and its surroundings, listening for the ground to crack. 15 stations inside the park, and more beyond it, take a satellite fix on their own position hour after hour, and will notice if the ground carrying them moves by a centimeter. Instruments cemented into boreholes feel the rock flex on the scale of minutes. Radar satellites map the rise and fall of the whole caldera from orbit. Gauges taste the rivers, sensors count the gas. And all of it is distilled for the public into a 4-word ladder: normal, advisory, watch, warning. In all the years that ladder has existed, Yellowstone has never once left the bottom rung. So the question from the parking lots, would anybody know, becomes a sharper one. What would those machines show in the weeks before a caldera let go that they have never shown before? No one has ever watched it happen. That has to be said plainly and once. What has been watched closely is a series of great calderas elsewhere coming to the edge of it, and their records are the nearest thing to a rehearsal transcript that exists. At Campi Flegrei, the caldera half buried under the outskirts of Naples, the ground beneath the town of Pozzuoli rose nearly 2 meters between 1982 and 1984, not centimeters, meters, while more than 16,000 earthquakes rattled the harbor. If you had stood on the waterfront there in those months, you could have watched the sea appear to retreat, because the land under your feet was lifting out of it. 40,000 people were moved away. Nothing erupted. The ground, having risen, simply stopped. At Rabaul, a caldera in Papua New Guinea with a town inside it, The floor rose and the quakes came in their thousands through 1983 and 1984. The alarms were readied, and again, nothing for 10 years. Then, in September 1994, the real thing arrived, and from the first violent swarm to twin volcanoes erupting on either side of the harbour took 27 hours. 30,000 people got themselves out overnight, on foot and by truck, largely because the town had rehearsed it for a decade, and 5 people died where thousands might have. Between those two stories lies the whole uncomfortable truth of caldera forecasting. Meters of uplift can mean nothing, and the eruption, when it finally chooses, can give you a day. The one great eruption where the instruments, the scientists and the decisions all worked in time was Pinatubo in the Philippines in 1991, a mountain so quiet that people farming its slopes did not know it was a volcano. Steam explosions opened it on the 2nd of April. A small joint team, Philippine and American, flew in with borrowed instruments, and through May they measured the sulfur dioxide drifting out of its vents, around 500 tons a day in the middle of the month, more than 5,000 by the 28th. A tenfold rise in a fortnight meant fresh magma was climbing, gassing off as it came, and the team convinced the authorities to act on a graph. A dome of new lava confirmed it in the first week of June. The first great blasts came on the 12th, and on the 15th of June the mountain produced the largest eruption anywhere in living memory, 9 hours of it, a cloud to some 40 kilometers in the middle of a passing typhoon. By then, roughly 60,000 people had been moved out of the danger zones, an air base among them, and the evacuations are credited with saving thousands of lives. From the first steam to the climax took 10.5 weeks. That is the entire span, one school term, in which the 20th century's greatest volcanic crisis was detected, understood, and survived. There is a fourth story, and it belongs in the ledger too. In the early 1980s, the ground inside the Long Valley caldera in California swelled by 1/4 meter and shook with swarms, and in May 1982, the survey did the responsible thing and issued a formal notice of potential volcanic hazard. No eruption followed. What followed was the slow wrecking of a town's economy. Visitors stayed away from mammoth lakes, businesses failed, property lost its value, and within 2 years something like 4 in 10 residents had gone. Signs reading "Geologists not welcome" appeared in shop windows. Every observatory on Earth carries that story because it marks the other edge of the knife. Speak too late and people die under ash. Speak too soon and you may break a town on a maybe. Set Yellowstone's rehearsal against all of this and the shape of the weeks emerges. The run-up would almost certainly not be subtle. A chamber fit to empty by the hundreds of cubic kilometers would have to grow and press and vent, and the plateau would broadcast it. Earthquake counts climbing from a quiet month's few dozen into the thousands, and then beyond anything in the record. The caldera's gentle breathing turning into a heave, millimeters giving way to meters, the satellite traces bending until you could read them from across a room. Gas flux multiplying the way Pinatubo's did, new ground boiling, new fractures steaming, the basins convulsing the way one night in 1959 showed they can. The word on the public ladder would climb rung by rung on television and in 100 languages. That much the machines would see and say, and no one on the continent would be unaware of it. What the machines could not say is the one thing everyone would ask. Right up to the last hours, no instrument yet built can be sure whether ground behaving this way is delivering a lava flow, a modest explosive eruption, or the floor itself. And the difference between those answers is the difference between closing a park and rewriting a continent's decade. The dread of that gap is specific, a screen full of perfect data and no sentence at the bottom of it. And however long the notice ran, weeks like Pinatubo's, a rehearsal decade like Rabaul's, even the full quiet decades written in the Lava Creek crystals, it would still be, on this ground's own calendar, no time at all. 600,000 years of stillness, and at the very end a few seasons of trembling, one breath drawn in at the close of a recording longer than our species. Somewhere in those imagined weeks, the page that has read normal since the day the page was made would finally show the last word it holds. Warning. What follows that word is measured not in seasons, but in hours. By the last evening, the word would have been on every screen on Earth for days, and the plateau below it would already be empty. That is worth picturing, because it is the opposite of every disaster we rehearse in the imagination. No lines of cars in the ash, no sirens under a black sky. The clearing out would have happened weeks back, in ordinary weather, on dry roads. The park is a place people visit, not a place they live, and a service that shut a whole basin over one exploded pool would have shut all of it at the first hard swarm. The gateway towns would follow early and grudgingly, and in the end completely, the way a town in Papua New Guinea once walked itself out overnight because it had rehearsed for a decade. What stays behind is the machinery. The seismometers would go on transmitting from an emptied plateau. The cameras would stream geysers erupting on schedule for an audience of instruments, Old Faithful keeping its appointments for nobody, while in rooms hundreds of kilometers away, the traces climbed. The end of the waiting would arrive on those traces as a change of key. For weeks, the ground would have spoken in separate cracks, thousands of small breakings a day, each one a sharp spike on the drum. In the final hours, at calderas that have been caught in the act, the spikes begin to run together into a continuous underground note, tremor, the signature of fluid forcing its way through rock rather than rock snapping, and the tilt meters swing smoothly off their scales, the flexing no longer episodic, but one long inhale. Where the crust finally parts, if the newest imaging of the underworld is any guide, would most likely be the caldera's northeast, because that is where the surveys of the last few years placed the richest of the molten pockets. And the parting would not be a single throat, but sections of the old ring coming open, the curved seams the floor moves along, unsealed for the first time in 600,000 years. What comes out first is a jet. Gas and foam of molten glass, decompressing as it rises, tearing itself into pumice and shards, and the speed of the thing is the part the mind resists. When Mount St. Helens erupted in 1980, its column stood higher than 24 kilometers within a quarter of an hour of the opening. A column here, by the survey's working range, would climb into the 30 to 50 kilometer band, which, by the line usually drawn at 100 kilometers, is a third to half the way to space, punched upward in less time than a commuter spends getting to work. The material driving it is strange stuff to hold in the head, rock frothed so full of gas that it comes out lighter than water. Pumice is the one stone you could float in a pond, and for the first hours it would fall in beds of grey foam, lying light as fresh snow on the ridgelines and thickening by the hour. Sound behaves strangely around eruptions of this class, and the strangeness is documented. In June 1912, when an event called Nova Rupta opened in Alaska, the detonations were heard in Dawson City and in Juneau, 1,000 kilometers and more from the mountain. Yet at the village of Kodiak, a fraction of that distance, people heard almost nothing before the cloud arrived, because the shock had stepped clean over them through the upper air. Much of what an eruption broadcasts is pitched below hearing altogether. Infrasound, pressure you would feel in the chest and the windows would feel in their frames, rolling outward for thousands of kilometers. And the cloud carries its own weather with it. The men who watched the 1912 eruption from ships and mission stations reported thunder and lightning through the ashfall, at times continuous, at times as ball lightning down near the ground, so intense that it burned out the region's new wireless stations, one of them to the ground. A column of grinding glass makes its own storm. Ours would be no different, only vaster. A stalk of lightning-laced grey standing over the Rockies, visible as a smudge from the coasts, its base wrapped in falling pumice, its top spreading flat against the stratosphere. Now, the tempo, because the tempo is where the old record speaks most directly, and what it says runs against every instinct trained by cinema. The two geologists who gave much of their working lives to mapping the 1912 deposits, Wes Hildreth and Judy Fierstein, reconstructed that eruption not as an explosion but as a sequence. 3 distinct episodes over roughly 60 hours, the largest eruption of the 20th century delivered in installments across 2.5 days. At Taupo in New Zealand, the most recent super eruption on Earth, 25,500 years ago, 530 cubic kilometers of magma, the deposits record 10 separate phases, spread across what their intervals suggest were months. And under this plateau, the first of the 3 great tuffs remembers exactly the same habit: pumice falling for weeks before the main collapse, then pauses between its members long enough, in one case, for the ash to weather and the land to begin repairing itself before the next phase buried the repairs. So the opening minutes we have been describing would be the start of something with movements, like a symphony scored for geologic patience. Hours or days of climbing column. A first fall of pumice across the northern Rockies. Then, perhaps, quiet. A morning, a month, conceivably longer, the trembling easing, the cloud thinning, the first grey hope that it was over. The record says the quiet is part of the eruption. Through all of this, the floor of the caldera would not yet have fallen. The first act belongs to the column, and for as long as it lasts, the eruption remains a thing of the upper air. Seen from orbit in those first hours, it would be almost serene. One white-grey pillar standing off the curve of the planet, its umbrella beginning to open, its shadow laid 100 kilometers across Wyoming and Montana, lightning firing inside it like a fault in a screen. The tallest thing the Earth can build, raised in an afternoon, and at that distance nearly silent. If you had been given the view without the story, you might have called it beautiful. Down at its base, along the unsealed sections of the ring, the character of the eruption was already preparing to change, because a column is only what happens while the sky can still carry everything the vents deliver. A column fails from below. As the vents widen and the discharge climbs, the jet at the base can no longer swallow enough air to keep the whole rising mass lighter than the atmosphere around it, and the eruption crosses a line drawn in plain physics. What goes up starts to be less than what comes out. The margins of the column sag first, then great sections of it fold and pour, and above the ring of vents the eruption turns into a thing with no everyday name, a standing fountain of glowing rock, kilometers tall, feeding floods that run away along the ground in every direction at once. This is the hinge of the whole day, and it deserves to be marked as it passes. From this hour, the eruption's product stops being weather and becomes ground. We are not guessing at what those floods are because their beds are open to the hand. Drive the park's roads and the pale rock standing in the cuts is fused ash. The grain of it under your fingers is glass, billions of shards pressed and welded while they were still soft with their own heat. Rock like that cannot be made by anything gentle. It is the settled body of what geologists call a pyroclastic density current, and the plain description is this: an avalanche of hot glass particles and gas, heavier than the air it displaces, ground-hugging, self-lubricated, riding on a cushion of its own churning. It is not lava. Lava crawls. It is not wind, though it moves like wind gone wrong. A dense undercurrent hugs the terrain while a boiling cloud of finer ash rides above and around it, and the two together behave like a flood that has been relieved of water's patience. The measured speeds start where road traffic ends. At Mount St. Helens, the currents were clocked between 80 and 130 kilometers an hour, and those were small ones, from a small stratovolcano having its one bad morning. The deposits of the great caldera eruptions record speeds several times faster than the fastest train you could ever have ridden. Fast enough that ridgelines hundreds of meters high did not turn them, only trimmed them. Their heat has been measured too, in the most somber of laboratories. In the towns Vesuvius buried in the year 79, the temperatures the deposits reached can be read from charred wood and altered bone. 180 to nearly 400 degrees through much of Pompeii. And at Herculaneum, closest to the mountain, an opening surge near 500, heat that charred roof beams in the moment of its arrival. Those were currents from an eruption thousands of times smaller than the one we are following. The caldera-scale currents ran hotter still. We know because their deposits fused, and ash only welds itself into rock when it lands glowing. Around the plateau, in this hour, the floods would pour outward from the whole unsealed ring rather than from one flank, and their reach is the reason the evacuation maps were drawn the way they were. The survey's own assessment puts it without drama. Flows from an eruption of this class would reach the parts of Montana, Idaho, and Wyoming that lie closest to the park. Inside that reach, the transformation would be total and quick. Forest taken at the speed of its own falling, rivers capped and turned to steam, soil, deadfall, snowpack, all of it swept up as fuel and cargo, and behind the front, silence and a settling sheet. Nothing caught inside a current survives it, and nothing about that sentence changes for size or speed or luck. It is why these events leave whole landscapes as a single layer. The distances involved would beggar the park itself. Currents running out beyond the rim by something like the length of the caldera again, farther than you could see from any high ground on its edge, filling the valleys of the surrounding ranges and lapping at the passes. And under the fountains, all this while, the drain is running. Here, the only instrument-grade rehearsal we own is the Hawaiian one, and its lesson bears repeating in sequence. As magma leaves a chamber faster than anything refills it, the pressure holding up the roof bleeds away, and the roof does not sag politely. It hangs on friction, storing the debt, and then pays it in lurches. At Kilauea in 2018, each lurch of the summit block also acted like the stroke of a plunger. Every drop of the pistons squeezed the chamber and drove a fresh surge out of the vents miles away, so that the collapse and the eruption fed each other in turns, the crater at the top gaping wider by the week until it had grown by more than 1.5 kilometers across. Scale that machinery up to a roof hundreds of times the area, over a chamber shedding not a fraction of a cubic kilometer, but hundreds of them, and you have the engine room of a caldera in formation, a block of crust the size of a small nation's heartland, stepping downward jolt by jolt, each step ringing through the continent's bedrock, each step ringing another flood out of the ring. This, finally, is the hour our whole story opened inside. The falling floor, the jolts written onto seismometers coast to coast, and it can now be set where it belongs in the order of the day. The column comes first and owns the sky. The failure of the column turns the sky's cargo loose along the ground, and the emptying that both of them draw on brings the floor down after, so that source, flood and collapse run together into a single self-consuming machine, the caldera swallowing the eruption that is hollowing it out. The three great tuffs of the plateau are each the fossil of exactly this hour, run 3 separate times, hundreds of thousands of years apart on this one patch of crust. By the end of it, the near field would already be unrecognizable and strangely becalmed. Where the currents have passed, there is no fire to see. Fire needs standing fuel. only a grey plain of smoking rock where the topography used to be, veined with steam, radiating like an opened oven, beginning the years-long work of cooling into the next generation of road-cut stone. The stillness of such a place, after a sound too large for ears to have held onto, is its own species of quiet. Above it, the column would still be standing, replenished with every stroke of the piston. Beneath it, the floor would still be going down, hundreds of meters of descent banked already, more to come. And overhead, spreading now far beyond the sight of anything on the ground, the grey lid at the top of the sky would have begun its own journey. Out over the ranchlands and the ranges, out over the cities of the Mountain West, dimming the afternoon into something the colour of weak tea. The first hour ends with the land remade for a day's walk in every direction. The night that follows belongs entirely to the cloud. Follow the cloud through that night and give up, straight away, the picture the word cloud suggests. Smoke drifts where the wind sends it. This would not drift. A column feeding an umbrella at the top of the sky, at the rates a caldera delivers, spreads under its own power, shouldering the atmosphere aside and pushing its edge outward in every direction, including into the wind. The modelling done on exactly this question found ash driven more than 1,500 kilometres westward, upwind, and as far again to the north and south. At this scale, the familiar logic of downwind and upwind simply stops applying. The cloud is not riding the weather. For a day or two over the middle of a continent, it is the weather. That modelling deserves to be introduced properly because the whole of this day rests on it. In 2014, 3 scientists with the survey, Larry Mastin, Alexa Van Eaton and Jake Lowenstern, put a Yellowstone-scale eruption through an ash transport model of theirs, feeding it 330 cubic kilometers of dense rock, an umbrella near 25 kilometers up, and a full year of real recorded winds, season by season. They ran it as a 3-day eruption, a week-long eruption, a month-long eruption, and found to their interest that the duration barely changed the map, the same material spread over the same country, whatever the tempo. What came out, in every season they tried, was not a plume-shaped stain angling off toward one unlucky compass point, but something closer to a bullseye, deepest at the center, leaning east, but touching everything. Decimeters to meters of ash across the northern Rocky Mountains, centimeters to decimeters over the northern Midwest, millimeters to a few centimeters on the coasts, the Pacific, the Atlantic, and the Gulf alike. Averaged over all their runs, the model's numbers for particular places read like this, and they are the model's numbers for one assumed eruption, not anyone's forecast. Billings, the nearest sizable city, about 1.5 meters. Casper, 0.5 meters. Salt Lake City, 1/4 meter. Denver, 10 centimeters, the width of a palm. Minneapolis, 4 centimeters. Chicago, 1.5 centimeters, a fingertip. San Francisco, just under 1 centimeter. Los Angeles, 5 millimeters. New York, 2.5 millimeters. Miami, 3,500 kilometers from the vents, 0.5 millimeter, the thickness of a coin split in two. Numbers like these carry 2 truths at once, and both need saying. They describe a single event dusting an entire continent, coast to coast, which nothing else on Earth can do, and they are, in the survey's own words about its own model, far less than most doomsday tellings of this story assume. No continent buried, no country entombed, but a great grey gradient, from meters near the crater to a film at the far edges. What it would be like to stand under the deep end of that gradient is not a matter of imagination either, because it has happened to a documented town in living memory at almost exactly the right distance. Kodiak, on its island off the Alaskan coast, sat 160 kilometers from the vent called Nova Rupta in June of 1912, much as Billings sits a little farther out from the caldera we are following. On the afternoon of the 6th of June, the revenue cutter Manning lay moored at Kodiak in clear weather when her captain, K.W. Perry, noted a peculiar-looking cloud rising slowly in the southwest. Distant thunder followed it. By 5, the ash had begun to fall. By 7 that evening, in Perry's words, a black night had settled down, hours before sunset. Through the night, the fall thickened, and by morning about 13 centimeters lay on the town. The streams and wells were already fouled with it, and the Manning had turned herself into the town's water supply, piping clean water ashore from her tanks. Then came the stranger lesson. Through the morning, the fall eased, and by 9 it had stopped. The sky stayed brown, but it was over. Anyone would have said so. At noon, it began again, heavier, and by 2 o'clock in the afternoon, the town was in pitch darkness, and it remained in pitch darkness for the next 24 hours. Not gloom, darkness at midsummer in the middle of the day, of a kind that made the ship's rail invisible from the deckhouse. 835 people came aboard the Manning or crowded into a warehouse on the wharf and waited it out, while the crew worked in shifts with shovels and fire hoses to keep the decks from loading up, and ash slides came hissing down the hills around the harbour, and the air, by the reports, carried strangling whiffs of sulfur. A third fall came and went the following evening. When dawn finally arrived clean on the 9th of June, Kodiak stood under 25 to 30 centimeters of settled ash, and the toll aboard the crowded ship, after 3 days at the center of all this, was one elderly woman, a refugee who had come aboard already gravely ill. The ash had taken the town's light, its water, its roads, and its nerve, and that one loss aside, no one had died. Kodiak's day is the closest thing on record to day 1 under the near field of our cloud, including its cruelest feature, the pause. The sky finished, and then began again. Anyone who steps outside when the light comes back has the record's word for it that the light coming back means nothing. For the middle distances, the 20th century logged a smaller rehearsal. When Mount St. Helens erupted on a May morning in 1980, its ash reached the city of Yakima before 10 and Spokane before noon, switching on the streetlights as it came, and by early afternoon Spokane, 400 kilometers from the mountain, stood in what the record calls complete darkness. 540 million tons of ash came down across 57,000 square kilometers in 9 hours. Fine ash crossed the United States in 3 days and circled the Earth in 15. That was an eruption roughly 1,000th the size of the one we are following. Multiply Yakima's morning across every town from the Rockies to the Great Lakes, deepen it by the model's gradient, and the first day assembles itself. Darkness at noon somewhere over several states, streetlights burning in a band 1,000 kilometers wide, and beyond that, hour by hour, the quiet arrival of grey on regions that never heard a sound. None of this is the model talking in the end. The continent has kept the receipts. A meter of this volcano's ash stands in a rock formation in New Mexico. A foot of the hotspot's ash lies under 250 miles of Nebraska, the same bed the rhinoceroses lie in, a day's fall preserved with its dead in place. A band of it the color of old silver waits in the creek banks of Kansas. The bullseye is already drawn on this continent, in stone 3 times over. The model only redrew it in the present tense. And at the far edge of it, on the evening of the first day, the strangest entry in the whole ledger, both oceans. On the Gulf, on the Pacific, on the Atlantic, on cars parked 3,000 kilometers apart, facing different seas, the same fine grey film would be settling, half a coin thick, light enough to wipe away with your sleeve in a single pass. Out there, so far from the falling floor that the ground never once trembled, it would be the easiest thing in the world to look at that film and call it nothing. What does 0.5 millimetre of powdered glass actually do? Because that is the honest name for the film on those cars. Volcanic ash has nothing in common with the soft grey word ash except colour. It is rock and glass milled fine in the column, hard enough to scratch steel, sharp at every edge, conductive the moment it gets wet, and it never melts, never rots, never goes away on its own. The engineers who compiled the world's accumulated experience of the stuff, power companies, water utilities, airport authorities, from every ashfall of the last century, arrived at a sentence worth reading twice. Falls of just a few millimeters are damaging and disruptive to electricity, water, roads and aviation, not meters, millimeters. The catastrophe near the crater is total but local. The genius of ash is that it exports failure to places that never hear the eruption, using quantities that fit in a teaspoon per square meter. Take the roads first, since everything else depends on them. At less than a single millimeter, painted markings disappear under grey, and the surface begins to behave as if lightly iced. Measured skid resistance starts dropping at 1/10 of a millimeter. Every passing vehicle throws the fall back into the air, so visibility collapses along exactly the corridors people are trying to use, and wipers make it worse. Drag them across a dusted windscreen and you are sanding the glass with every stroke, frosting it a little more each pass. Nothing is destroyed. Everything slows, then stops across whatever area the map has shaded. And the model's shading, remember, runs coast to coast. The sky shuts faster than the ground. Jet engines run hotter than the melting point of volcanic glass. So an aircraft that flies into an ash cloud is feeding its turbines, a material that liquefies in the combustor and freezes again on the blades as glaze. The world learned this in the most direct way available. In June 1982, a British Airways 747 flying overnight near Java entered a cloud no radar had painted, and all 4 engines failed at 37,000 feet. The crew glided the aircraft down through thousands of meters of night before the engines, cleared by the cold airflow, could be restarted one by one and landed safely in Jakarta. 7 years later, over Alaska, a KLM 747 repeated the entire sequence almost exactly, down to the safe landing. The global ledger from 1953 to 2009 records 129 encounters between aircraft and ash, and 9 of them involved engines failing in flight. No passenger has died of one, and the reason is a rule written in those cockpits: aircraft and ash are never knowingly allowed to meet. Which is why, in the spring of 2010, a modest Icelandic eruption, less than 1/5 of a cubic kilometre of magma, all told, emptied the sky over Europe for the better part of a week. More than 300 airports dark across a couple of dozen countries, around 100,000 flights cancelled, 10 million travellers stranded, all of it precautionary, almost none of it under falling ash. Now lay that rule over the first day's map, with the cloud standing across the busiest overflight country on Earth. The grounding would be continental within hours, and it would hold for as long as the column fed the sky. On the ground, the quiet failures would compound. Wet ash conducts electricity, and the high-voltage insulators that keep transmission lines apart from their towers are designed for rain, not for rain mixed with conductive grit. When Chaiten, a rhyolite volcano in Chile, the same rock as this one, erupted in 2008, stations sitting under 5 to 10 centimeters of its ash suffered flashover after flashover, and some insulators simply burst. A grid can be brought down by millimeters and drizzle, and every crew sent to wash the hardware travels on the roads we have already closed. Water systems fail at both ends at once. Intakes pull in a suspension so cloudy that disinfection can no longer be trusted. Fluoride leaches off the fresh glass into supplies, and on the demand side, an entire region turns on its taps and hoses to wash the grey off everything it owns. just as treatment falters. Kodiak's wells went in a single day, and Kodiak was a village with a ship alongside. There is no cutter big enough to moor beside the Midwest. And then there are the roofs, which is where the numbers turn grave. Dry ash weighs 500 to 1,500 kilograms the cubic meter. Rained on, up to 2,000. The load can double with one wet night. Roofs begin to fail above 10 centimeters of the stuff, commonly above 30, and it helps to feel what those figures mean. 10 centimeters of wet ash is on the order of 100 to 200 kilograms pressing on every square meter, more than you could lift, repeated across the whole span of a building. This is where the picture most of us carry needs correcting, and it deserves a fair statement first, because it seems so reasonable. Ash, therefore lungs, therefore choking. Surely breathing is how an ashfall kills. The record is emphatic the other way. Ashfall, the survey's own health pages say, rarely endangers human life directly. It inflames eyes and airways, and it is a real menace to those already ill, but healthy lungs ride out days of it. What killed several hundred people at Pinatubo in 1991 was weight. A typhoon crossed the region in the hours of the Great Eruption. Rain loaded the fresh fall, and roofs came down across the provinces. More than 100 buildings collapsed on one airbase alone, and the observer's verdict was blunt. Most of those roofs would have held if the sky had stayed dry. Under this cloud, somewhere between the meter band and the centimeter band, that arithmetic would be running on millions of buildings at once, with one merciful difference. Almost everyone would be reading it from outside, because the deep bands would have been emptied of people long before their roofs went. The rivers keep their own schedule. In 1980, ash and debris washing off the St. Helens country shoaled the Columbia's shipping channel from 39 feet deep to less than 13, and ocean freighters upstream were simply trapped. That was one river taking the wash of one small eruption, and the dredges worked for years. 1,000 miles of Washington's highways closed that same week. Multiply by the model's gradient, and the continent's midsection becomes, for a while, a place where bulk anything, grain, fuel, ore, cannot reliably move by road, rail, or water at once. Here, the grammar of this story has to be watched closely, because it is doing load-bearing work. Every threshold above is a wood, measured, published engineering fact. What nobody has ever measured is all of it together, every failure mode firing simultaneously across the middle of a continent for weeks, with the repair crew's own runways and substations and water mains sitting under the same grey. And so the sum, unlike the parts, is an honest could, a place where the record simply ends. What can be said is that 631,000 years ago, this same week fell on a continent that owned nothing breakable. No wire, no pane, no pump. The only machinery under that sky was lungs and legs, and the bed it left is a quiet silver band in a Kansas creek. The fragility is the new ingredient. We brought it. By the third or fourth night, the failures would have found their rhythm, and somewhere out in the centimeter band you could watch the week distill itself into a single image. Rain starting over a dark county, a transmission tower standing in it, wet grey paste creeping across a string of insulators, then one violet arc bright as a camera flash over land that has gone entirely quiet, and the same rain falling past the tower onto field after field after field. The animals go the way the grass goes, and that story has already been written down once, in full, with the bodies left in place, at the waterhole in Nebraska where we began the walk back. 12 million years ago, the first month after an ashfall was recorded there the way a camera records, and before this month of ours is over, we will need to read that record properly, right to its end. But it helps to come at it the modern way first, through the farms, because the 20th century ran 2 experiments on exactly this question, and their results point in opposite directions. The thresholds themselves are published and plain, A dusting of a few millimeters on cropland is survivable and sometimes barely matters. Push past 10 to 15 centimeters and the agronomists stop hedging. Pasture and standing crops are severely limited, which is the dry way of saying buried, flattened or starved of light until they fail. In between lies a gradient of harm that depends on the crop, the week of the growing cycle, and above all, on rain. And for grazing animals there is a separate, crueler line in the table. Ash carries fluoride on the surface of every fresh grain, and a coating as thin as 1 millimeter on grass can poison the animals that eat it. 1 millimeter. Lean on a fence and look out across a pasture wearing that much, and you could not tell it from a dry morning's dust. The first experiment was Mount St. Helens, and its results surprised the people who ran it. The 1980 ash came down on the wheat and orchards of eastern Washington in fields of centimeters, in the middle of the growing season, and the early talk was of ruin. A team of agricultural scientists led by R. James Cook spent that summer measuring instead of talking, and published the tally in Science within the year. Losses of about 7% of a normal harvest. Wheat came in ordinary or better. So did the potatoes and the apples, helped by a stretch of kind weather that offset the shading. The alfalfa went down. 30 kilograms of ash on every square meter of a leafy crop simply pressed it flat. But the flattened hay turned out to be harmless to the cattle that ate it. The insects took it worst. Bees and grasshoppers died wholesale, cut up from inside by the glass they groomed off their own bodies. The lasting cost was duller than catastrophe. Engines eating grit, extra passes of the plough, machinery aging years in a season. Farming under a centimetre of ash, it turns out, is farming with sandpaper in everything, and it mostly goes on. The second experiment ran in Iceland 2 centuries earlier, and it is the one that keeps agronomists careful. In 1783, a fissure called Laki opened and erupted for the better part of a year, and with the lava came gas and fine ash freighted with fluorine, more than 7 million tons of it settling onto the island's pastures. The grass grew poisoned, and the animals ate it because there was nothing else. Half of Iceland's cattle died, 3/4 of its horses, nearly 4/5 of its sheep. And in the famine that followed the herds down, roughly 1 Icelander in 5 died. Not of ash in the air, not of anything so direct, but of the slow arithmetic of a small country whose food had been standing in a field at the wrong time. Set Laki's proportions against any herd you can picture. Of every 5 sheep, 1 left standing, and the difference between a dusted farm and a poisoned one becomes the difference between a bad year and a broken decade. Which of those 2 stories the month after our eruption would tell depends on where you stand under the model's gradient, and on a fact this account has deliberately left unfixed: the date on the calendar. The same fall on the same county is a nuisance in November stubble and a catastrophe in July wheat. What can be said with the modelling in hand is that the deep bands, the meter country, the half-meter country, would be out of production regardless of season, their pastures buried past the reach of any grazing animal, and their fields unworkable until the ash is moved or mixed. That the centimetre belt across the Midwest could, with luck in the weather, have a St. Helens month, diminished and gritty but alive, and that between them would run a wide fluorine country, fields that look merely dusty and cannot safely feed a herd, where the month's real work would be the moving or the culling of animals on roads we have already seen made slick and blind by the very material that poisoned the grass. A continent's midsection idled or hobbled for 1 growing cycle is not famine. Granaries and imports exist for exactly this. But it is the first month in which the eruption stops being a story about a place and becomes a story about a season. And the season is what the waterhole in Nebraska preserved, in the oldest and most complete version we possess. Picture that country in the weeks after its ashfall. Not buried, most of it, a foot deep on the flats, remember, drifting like dry snow, but resurfaced, every leaf gritted, every stream running grey, the wind lifting yesterday's fall and laying it down again somewhere new. The water in the low places drew everything alive. They came and stayed, cranes, turtles, small camels, three-toed horses and the barrel-bodied rhinoceroses, drinking clouded water, grazing glassed grass, breathing whatever the wind was carrying that day. And then they began to die, in strict order of size. The small lunged things went first, the birds and the little mammals, within days. The horses and camels held out longer. The rhinoceroses, with the great slow lungs of their bulk, lasted weeks and in some cases months. And we know that not from guesswork but from their skeletons, because dying slowly of the lungs leaves a signature. Starved of oxygen over weeks, the body lays down abnormal lacework collars of new bone along the limbs, a pathology veterinarians still recognize, and it is all over the ashfall herd. You can read the whole month off their bones, not a burial, not a blast, but a landscape that had become very slightly unbreathable, killing its largest tenants last, beside the water they would not leave. The calves lie next to the cows. That is what a first month looks like when nothing at all is done. No roads, no culls, no feed trucked in from beyond the grey, no veterinary line drawn around the Florine country. It is not a picture of our month. It is the floor under it, the unmanaged case, 12 million years old and holding still. Between that floor and the Washington wheat harvest lies the whole space where the aftermath would actually be decided, farm by farm, county by county, in 10,000 undramatic decisions about hay and water and which animals to move first. But every one of those decisions, from the rangeland to the grain exchanges, would be made under a single shared assumption, that this is one lost season. Fields recover from a year. Herds are rebuilt in a few. The entire recoverable version of this month rests on the sun coming back next spring with its usual strength, and whether it was being settled during these same weeks, far above the fields and the weather alike, by something that left the vents in the first hours and has not come down, a gas with no colour, no smell, and a longer reach than all the ash on the continent. 25 kilometers above the fields, in air too thin and dry for weather, the eruption's longest-lived export would already be at work. Alongside all its rock, a caldera eruption pumps out sulfur dioxide by the millions of tons. Call it colourless and, at these dilutions, scentless. Though near the vents, it stings like a struck match, and in the stratosphere that gas does not stay a gas. Over weeks it reacts with water into droplets of sulfuric acid, finer than fog, and those droplets do two simple things with enormous consequences. They scatter a share of incoming sunlight back into space, and they refuse to come down. Ash falls out of the sky in days. The sulfate veil rides above the rain, above everything that cleans an atmosphere, for 1 to 3 years, circling the planet on the stratospheric winds. In the survey's own summary of what governs a great eruption's reach into climate, the residence time of that sulfate is the paramount controlling factor. Not the ash, not the size of the hole in the ground, the sulfur and how long it hangs. We know the exchange rate because the 20th century measured it end to end exactly once. Pinatubo in 1991 lofted 17 to 20 million tons of sulfur dioxide, and James Hansen's climate group, reading the satellite gas maps within weeks, predicted publicly what would follow: a global cooling of about 0.5 degrees Celsius. The planet then performed the experiment. Temperatures sagged, bottomed out roughly a year and a half after the eruption at very nearly the predicted number, and recovered over 2 to 3 years as the veil thinned. 0.5 degree sounds like nothing. Averaged over an entire world, it is a vast quantity of missing summer. The early 19th century ran the harder version, Tambora, in Indonesia, erupted in April 1815 with tens of cubic kilometers of magma and several times Pinatubo's sulfur, and the following year became, in the folk memory of two continents, the year without a summer. Snow fell on Albany, New York, on the 6th of June 1816. Killing frosts kept returning to New England through the growing months. Grain failed across war-exhausted Europe, and in Indonesia, where the ash and the waves had already done their work, famine and disease in the aftermath took 71,000 people or more. The hemisphere's summer that year ran the better part of a degree cold. That is all it took, one lost degree in a world living harvest to harvest. Laki's haze, a generation earlier, had already taught Europe the same lesson in a dimmer key. 2 or 3 chilled years under a pale sky from an eruption most Europeans never learned the name of. So the arithmetic seems to right itself, and for years it did. If 20 million tons buys half a degree and Tambora's load bought a famine summer, then surely 1,000 cubic kilometers of erupting rhyolite buys the end of agriculture, 10 degrees of winter, a civilization-stopping night. That reasoning built the popular Yellowstone apocalypse, and it deserves to be stated fairly, because it is not foolish. It is a straight line drawn through 2 good data points. Early climate models of the greatest eruption in recent geologic time, Toba in Sumatra 74,000 years ago, drew exactly that line, some of them arriving at worldwide cooling of 10 degrees and more, and out of those numbers grew a famous idea that Toba's winter had nearly exterminated our species, squeezing humanity through a bottleneck a few thousand people wide. The line, it turns out, bends. It bends for a reason of pure physics, caught by the modelers who looked closest: droplets. Feed 100 times Pinatubo's sulfur into the stratosphere and the droplets do not stay Pinatubo-sized. They collide, merge, and grow. And larger droplets both scatter sunlight less efficiently, ton for ton, and fall out of the sky far sooner. The veil saturates. A German group that built this into their Toba simulations found the cooling capped near 3.5 degrees globally. Severe, but a fraction of the straight line answer, fading over 9 or 10 years. A NASA-led study in 2024, with still finer treatment of the droplet physics, concluded that even the largest eruptions probably cannot force the global average down by much more than 1.5 degrees. The honest range for the year after our eruption then reads, a global cooling somewhere between about 1.5 and 3.5 degrees, deepest in the second summer, skewed hard into the northern hemisphere, relaxing over most of a decade. And the bend is not just theory, because Toba left witnesses. In the mud beneath Lake Malawi in East Africa, coring teams found the eruption itself, a layer of Toba glass finer than a hair, 7,000 kilometers from the vent. Above it and below it, the lake's own thermometers, the algae, the chemistry of the sediment, carry on essentially unbothered. No collapse of warmth, no die-off in the waters. The paper's verdict was blunt: no volcanic winter in East Africa. On the South African coast, at a place called Pinnacle Point, archaeologists traced Toba's ash through the floors of inhabited rock shelters and found the human record running clean through it. The same tools, the same shellfish dinners, before, during and after the greatest eruption in 100 millennia. Whatever thinned our ancestors' numbers in that age, the ground refuses to blame the volcano. The newest models close the circle by adding geography to the droplets. Strong cold, yes, for years, but uneven with sheltered regions, southern Africa among them, where life would have registered strange skies and gone on, which is in fact what the shelters show. Held against the fields of the first month, this becomes the shape of the first year. Not darkness, nothing like it. The veil is a dimming measured in percent, not an eclipse. A northern growing season arriving late and leaving early, by 1 degree or by 3, over a grain belt already idled by grey. Frost showing up in the wrong months, the way it did in 1816. The surveys page on this subject says what can be said, weather patterns altered, agriculture affected, plausibly for 1 to 2 decades, and then adds the sentence that matters most, which is that no one has the predictive ability to pin down the specific consequences or how long they would last. That is the admission at the center of this whole chapter, and it is better than the alternative, because the field has stopped pretending. The bounds are real, bigger than Tambora, smaller than the apocalypse, for years rather than forever. 1 degree is worth learning to feel, and the strange truth is that it cannot be felt. Stand outside in a world 1 degree cooler and your skin reports nothing. Wheat, which cannot step indoors, reports everything. The nearest reference is already in hand. Over the course of your own lifetime, the world has warmed by about 1 degree, and you did not feel that either. You saw it in seasons, in snow lines, in dates on a calendar. This would be that, run backwards, arriving in 18 months instead of 80 years, and then, unlike our warming, letting go. An ice age, for the record, is not on the menu and never was. Ice sheets are built by tens of thousands of years of orbital arithmetic, by snow surviving summer after summer after summer. A decade of haze cannot found one, and no super eruption in the geologic record ever tipped the planet into ice that was not already coming. The veil rains out. It always has. The sunsets go extravagant for a year or 2. The one gift these events reliably leave, documented after every great eruption. And the curves bend back toward the ordinary. The second winter after our tomorrow would likely close colder than the first, but cleaner. Snow falling white on grey, the sky exhausted of its cargo, the thermometers beginning, quietly, to come home. After that, the story stops being measured in seasons at all. There is a plant that makes its living on ruined ground, and it reached the slopes of Mount St. Helens before almost anything else dared. When the 1980 eruption was over, the 6 square miles nearest the crater had been buried so deep and scoured so hot that the ecologists who walked it called it practically sterilized. The Pumice Plain, a name that was simply a description. No soil, no seed bank, no insect life. A surface, not a place. And then, within a couple of summers, researchers crossing that grey found prairie lupines in flower. Small, low, blue-purple, absurd against the pumice. The lupine's trick is that it carries its own fertility. Its roots partner with bacteria that pull nitrogen straight from the air, so it needs no soil worth the name, and every plant that establishes becomes a maker of soil for everything that cannot. Leaves catch drifting dust and hold moisture. Insects arrive, die, and add their small chemistry. Each lupine is an island the size of a dinner plate, and the islands spread. One ecologist, Charlie Crisafulli, marked out a study plot on that sterilized plain and simply kept returning to it, and within a decade his plot held more than 27 plant species. Kneel at a lupine on ground like that, and you are looking at the entire machinery of return running at its smallest scale, unbothered by the size of what it has to undo. Yellowstone ran its own version of the experiment before that decade was out. In the summer of 1988, fires burned 793,000 acres of the park, 36% of it, better than 1/3 of the map shaded in a single season, and the coverage of the time reached instinctively for the language of loss. The park destroyed, the crown jewel gone. The lodgepole pine had other information. A share of every lodgepole's cones are serotinous, sealed shut with a resin that lets go only in heat far beyond anything an ordinary summer could supply. So the forest had spent decades banking its next generation against exactly this. Cones waiting years in the canopy for the one temperature that means both death and instruction. The fires killed the parents and sprang the vaults in the same hour. Seedlings came up through the char in their millions the following summers, and the even-aged young forests standing on those burns today are ones you could walk through without ever guessing what planted them. Is recovery even the right word, though? It deserves the question because what returned in both places was not what had been there. The Pumice Plain has not gone back to being the old fir forest, and may never. It has become a different, younger, stranger community with its own residents. The 1988 stands are lodgepole in ranks, thick as hair, unlike the varied old forest they replaced. Give them 3 centuries and they will be unlike their replacements too. The land does not go back. It goes on from wherever it finds itself, with whatever arrives first, which is a gentler fact than restoration, and held long enough, a larger one. Because the crater itself has done all of this before, at a scale that makes the Lupine look instantaneous. After the floor fell for the 3rd time, the wound we have spent this whole story inside was healed the only way geology heals anything. It was resurfaced. The thick lavas came, eruption after eruption across hundreds of thousands of years, paving the collapse with the plateaus the roads now cross. A lake settled into the low ground and has been tilting gently on the breathing floor ever since. Forests took the flow tops as fast as the rock could rot into the first centimetre of soil, and the hydrothermal plumbing reassembled itself into 10,000 vents, until the scar of the most violent thing this continent does became the calmest place most visitors will ever stand. A burned forest reassembles in a century. The crater's own refilling ran something like 1,000 times longer. Same process, same direction, one more 0 on the clock. And the ash that went east had its own afterlife. Pressed under the prairie, it became a quiet layer in other soils, and in Kansas, eventually, a thing to quarry and scrub pots with. For the people of the years after, the honest grammar is might, and the precedents are at least pointed the right way. Kodiak washed out its wells, shoveled its streets, and is a working town today with the 1912 ash still in its garden dirt. The Columbia's shipping channel was dredged back foot by foot until the freighters returned. Around Pinatubo, the aftermath was longer than the eruption by years. Every rainy season remobilized the ash into rivers of grey mud, and it took the better part of a decade for the slopes to settle and green. But settle and green they did. On that pattern, the far bands of our continent-wide fall might be washed and repainted within seasons. The centimetre belt might, like eastern Washington, bring in a fair harvest the very next year and grumble about machinery for 10. The half-metre country might stand quiet for years, its towns reoccupied street by street as roofs are cleared and water runs clean, its roads ploughed of ash the way snow country ploughs winter. The deepest bands and the welded sheet at the centre belong to another calendar entirely. Decades, then centuries. And about them the record offers one strange, consistent prophecy. When explorers finally reached the valley that the 1912 currents had buried in Alaska, it was still steaming from thousands of vents, and they named it, in plain astonishment, the Valley of 10,000 Smokes. Within a few years, the United States had bounded it and protected it, and people have been traveling to stand in it ever since. You can walk into it today. That is what our species has reliably done with the aftermath of the Earth's greatest violence. We do not flee it forever. We fence it, name it, and come back to stare, the way we already did once, a century and a half ago, with the caldera itself. So the years after might read less like an ending than like the slow reversal of everything this account has described. The sky first, clean within a few years. The coasts and cities next, then the farms, then the towns of the grey belt, then, last and patient, the centre. Lupine logic working inward, island by island, toward ground that will not be ordinary again for centuries and will be visited long before it is ordinary. And all of it, every acre of that long return, would be standing on the same foundation the present park stands on. The lavas that sealed the last wound, 600,000 years of quiet stacked on top of them, forest and lake and boardwalk resting on the roof of the thing that did all this. Which leaves the question this whole story has been circling since the arithmetic of the 3 dates first came apart in our hands. Under those healing flows, under the geysers and the tilting lake, what exactly is down there tonight? The answer has been arriving in layers, one instrument at a time, over the last decade, and it is the best news in this whole long story. In 2015, a University of Utah team assembled years of earthquake recordings into the first complete portrait of the volcano's insides, and the picture came out 2 stories tall. The upper story is the one everything above ground answers to. A body of rhyolite roughly 10,000 cubic kilometers in volume, sitting a handful of kilometers beneath the caldera. Below it, reaching down through the crust, they found a second, far larger body of hot basalt, some 46,000 cubic kilometers, 4.5 times the size of the upper reservoir, the furnace room that keeps the geysers in business. 2 numbers came with the portrait, and they are the 2 that matter most. The great deep body was about 2% molten. The upper reservoir, the one that erupts, was about 1/10. Hold that against the picture most of us grew up with, because the old picture deserves a fair burial. The cross-section in every classroom and every disaster film showed a chamber in the literal sense, a red cavern, a lake of fire under a thin stone roof, full, waiting, needing only a crack. It was an honest guess once. The word chamber practically drew it for us. But every survey that has ever actually looked beneath this caldera has found the same thing instead: crystal. A magma reservoir at rest is a hot sponge of interlocking crystals with melt dispersed through its pores. Mush, in the unglamorous term of art, and mush does not erupt any more than a brick of damp sand pours. For rock like this to move, the molten fraction has to climb past something like 40%. 2% sits at the bottom of the volcano. 10 sat that year at the top. The portrait has only sharpened since. In 2022, a group ran 2 decades of seismic records through a far finer lens and found the melt gathered mainly between 3 and 8 kilometers down, richer than the first estimate, 16 to 20% at its peak. And the survey's commentary on the result made the point that matters. Nothing new accumulating, nothing on the move, a sharper photograph of the same sleeping subject. In 2025, another team mapped the ground's electrical conductivity, which molten rock raises and cold rock does not, and resolved the blur into 7 distinct melt-rich bodies stacked and scattered between 4 and 47 kilometers deep. The richest store of rhyolite melt, 400 or 500 cubic kilometers of it, threaded through the crystal framework, lies under the caldera's northeast, which is exactly why, when this story needed vents, it opened them there. And the author's own conclusion about all of it was flat, not eruptible at present. Nothing anywhere in the imaged system reaches even 20% melt in a material that will not move below roughly 40. The finest measurement of all took a heavier instrument than an earthquake. Across the nights of one summer, a 24-ton survey truck rolled along the caldera's roads, shaking the pavement in precise bursts, while some 600 portable seismometers listened to the echoes. And in 2025, the analysis came back with something no one had ever pinned down: the exact top of the magma reservoir, 3.8 kilometers beneath the surface, a distance you could walk in under an hour if the walk went straight down, and sharp, a transition thinner than 100 meters. The cap itself read as 86% solid, and the fluid in its pores turned out to be half melt and half bubbles of superheated water. That last detail is the quiet headline of the whole decade. The bubbles are not accumulating under a seal, the way they do in a volcano loading toward violence. They are leaking steadily upward, feeding the boil above. The tens of thousands of tons of gas the park exhales every day are this exact breath, caught at its source. The system is venting itself. A volcano that breathes out does not hold its breath. So the question left hanging over the lavas, whether we live in one of this system's eruptible ages or one of its long crystalline sleeps, now has an instrumental answer. This is the sleep. The reservoir under the park tonight is the cooling remnant Mark Stelton read in The Youngest Flows, mostly stone, growing more stone by the century, exhaling as it goes. What could wake it, and on what schedule, belongs to the one genuinely open argument left. Whether the heat below is delivered by a plume rooted at the planet's core, as the 2018 imaging drew it, or manufactured far shallower by the stresses of the plate itself, as the 2026 study in Science contends. That dispute will decide the volcano's biography, and perhaps whether the fading rhythm along the old track, the threefold slowing, is age or merely a pause. It does not move a single number under the park tonight. And the numbers under the park were never the ones the fear was built from anyway. The fear was built from arithmetic, the false clock of every 600,000 years. And it is worth hearing how the survey itself handles the sum. Average the two unequal intervals, and you get about one chance in 730,000 of a caldera-forming eruption in any given year. The agency publishes that number and, in the same breath, points out that it comes from simply averaging two gaps, which is, in its own words, hardly enough to make a critical judgment. Their working conclusions are stated without hedging. The chances of such an eruption are exceedingly small in the next few thousand years, and they see no evidence that another cataclysmic eruption will occur at Yellowstone in the foreseeable future. Stretch the annual figure across an entire 80-year human life, and it comes to roughly one chance in 9,000 for the least likely thing this ground can do, resting on a reservoir that is currently incapable of doing it. The planet as a whole runs warmer odds. Across all the world's calderas together, one recent catalogue puts a super eruption somewhere on Earth at about 1 per 17,000 years. That is the Earth's number. It is not Wyoming's, and folding the two together is how headlines are made. It is worth remembering, finally, how young the fear itself is. The science here runs back through Christensen's 6 summers to Boyd's welded tufts, patient decades of it. The word that turned this place into an apocalypse, supervolcano, was coined for a television documentary broadcast in the year 2000, and the geologists mostly took it up afterwards with a shrug because the public now owned it. The dread, in its familiar packaged form, is younger than the science by half a century, and through all of it, the coinage, the documentaries, the decades of headlines, the public alert scale for this volcano has displayed one word, the lowest it has, without a single day's exception. Which leaves the day this story began with exactly where the evidence puts it, not impossible, and not near. For that morning ever to arrive, the sponge would have to remelt several-fold, and assembly the crystals say takes years to decades of reheating that no instrument on the plateau could miss, announced in meters of uplift and seismicity beyond anything in the record. The unmistakable weeks we walked through. None of it is underway. What is underway tonight and every night is centimeters of breathing, a few dozen small earthquakes a month, and a thin, continuous thread of gas rising from a cap of crystal 3.8 kilometers down. The volcano asleep on its own slow exhale in the dark under the boardwalks, holding still. Close your hand around a flake of black glass. It sits cool against the palm, lighter than stone has any right to be, and its edge, where it was worked, is finer than anything a steel blade can hold. Obsidian fractures down toward the thickness of molecules, which is why surgeons have sometimes preferred it to scalpels. This particular glass began as the same molten rhyolite this whole story has been circling. About 180,000 years ago, one of the flows that came after the Great Collapse pushed out across the park's north side so thick and so dry that it could not build crystals as it cooled, and set instead as a cliff of black glass. Obsidian Cliff, the maps call it now, with their usual efficiency. People found it almost as soon as the ice left the plateau, and they never forgot where it was. The quarrying there runs back on the order of 11,000 years, older than agriculture, older than any standing building on Earth, generation after generation climbing to the same dark seam because nothing else in 1,000 miles took an edge like it. And then the glass began to travel. Around 2,000 years ago, the mound-building people we call the Hopewell, living along the river valleys of what is now southern Ohio, began acquiring Yellowstone obsidian in quantity, moved eastward hand to hand or fetched by expedition, nobody knows which, across some 1,500 miles of continent as the crow flies. They did not use it for hunting. They made it into ceremonial blades, some of them astonishing. One worked piece runs longer than your forearm. And they buried it with their dead. Under a single mound at the Hopewell Mound Group, excavators found roughly 300 pounds of obsidian fragments. A neighboring mound held close to 150 finished blades and points. For most of a century, archaeologists could only suspect where it had all come from. Then, in 1969, samples went into a reactor to be read by neutron activation, element by element, a chemical fingerprint, and the fingerprint matched one place on the continent, the cliff on the plateau. 3/4 of all the obsidian ever recovered in the eastern United States lies in that one Ohio county, and it is Yellowstone, carried there by hand, treasured, and laid in the ground with the beloved dead. Which means the volcano's most recent great export was not ash at all. It was beauty, and people walked it across a continent. The first scientific description of the cliff itself was written in 1888 by a survey geologist named Joseph Iddings, who recognized in its columns and its glassy sheen a textbook case of rhyolite cooling too fast to build crystals, and who was, without knowing it, standing in a quarry that had already been worked for 100 centuries. That is the braid this place keeps weaving. The oldest human economy on the plateau and the youngest science on it are handling the same rock. A hunter rough-shaping a core at the foot of the cliff. A Hopewell artisan pressure-flaking a blade too beautiful to use. A geologist in a wool coat sketching columns for a government report. A technician in 1969 feeding a sliver into a reactor. One unbroken chain of people, 11,000 years long, each of them holding the volcano in one hand and asking, in the idiom of their own age, what it is and what it can tell them. That is the fact worth holding while we come finally to what the science cannot yet say. 3 honest unknowns stand at the end of this story, and they deserve to be stated as plainly as everything else has been. The first, whether the reservoir under the park will ever again assemble a body of magma fit to erupt. The system has alternated before, long crystalline sleeps, shorter wakeful ages, and the instruments can read only the present, which is sleep. They cannot read the schedule because there is no schedule to read. No one knows whether the next eruptible age is gathering slowly somewhere below the imaging's reach, or whether the last one, 70,000 years cold, was the last. The second unknown sits deeper. What feeds this place at all? A column of heat rising off the boundary with the planet's core, says one careful body of work. The grinding mechanics of the plate itself, says another, published only recently. And both cannot be right. The dispute will take years to settle, And until it does, the volcano is in the strange position of being the best monitored on Earth and still uncertain of its own parentage. And the third unknown is the largest, whether the whole 16-million-year enterprise is ending. The eruptions along the track have slowed threefold. The continent's slide is carrying the melting zone northeast out from under the park at a few centimeters a year in toward the Beartooth country and central Montana, into some of the oldest, thickest, coldest crust the continent owns. Rock that has resisted everything for billions of years and may simply refuse to melt. Perhaps a few million years on, there will be a new line of calderas under Montana. Perhaps the line stops here, and Yellowstone is not the latest of its kind, but the last. That question will be answered over the next 10 million years, with perfect clarity to no one. Either way, the future of the park itself is already written in the plain that runs behind it. One day, 10,000 centuries from now or 100, the heat will have moved on or given out, and this plateau will go the way of every burned-out oven down the line, the ground cooling, the breathing stilled, the 10,000 hot mouths closing one by one until, on some morning no one can schedule, the most famous geyser on Earth misses an appointment and never keeps another. The lake will settle onto a floor that has finally stopped moving. Forest or grass or whatever grows in that distant climate will close over the last of the steam, and Yellowstone will become what Idaho already is. A quiet, productive, unremarkable stretch of country with a giant asleep under the wheat, visited by no one, because there will be nothing left to see. The wonder of the place, it turns out, was never permanence. It is that we happen to be alive during the eye blink when the fire and the surface are still touching. Hold the scale of that luck for a moment. Out on the lake, in a drifting boat, you are floating on the roof of the whole apparatus, the crystal sponge, the exhaling cap, the two-story furnace below it, and the roof is rising and settling beneath the hull, a handful of millimeters a year, too slowly for any sense you own to register. The trees drowning in the southern arms know. The rapids know, where the river had to cut through ground that kept lifting. The whole of written human history, every empire and alphabet, fits into the quiet since this floor last fell about 120 times over. We asked at the start what would happen if that quiet ended tomorrow, and the record gave its long answer. The column, the falling floor, the grey continent, the cold summer, the lupines, the return. But the record's deeper answer was about the question itself. Tomorrow is a human-sized word. This ground does not have tomorrows. It has ages, and it spends them the way we spend seconds, and it is currently spending one of the gentlest it has ever had directly underneath a boardwalk full of people photographing a geyser. Widen once more, as far as the story allows. Seen from that height, the whole continent is annotated. A meter of grey standing in a New Mexico rock face. A foot of it under 250 miles of Nebraska grass with a herd inside. A silver band in the Kansas creeks, 3 fires deep. Cores off the California coast and the Gulf's deep mud thickened with river-carried glass. Every one of those marks was terror once, by any measure a living thing could apply, and every one of them is now simply information, lying quietly in the ground, waiting for whoever thinks to look. The rapids on the Yellowstone River run where they run because the floor beneath them kept lifting. The trees drown where they drown because the lake leans. The boardwalks steam because 4 kilometers down the crystal is still warm. Nothing about this place hides. It is the most legible violence on Earth, written out at continental size in a hand that takes a century or two to learn. And we learned it, most of it, inside the lifetimes of people who are still alive. It is worth saying, before the lights go down, what all this reading has actually been. The Earth keeps no diary. The ash beds, the welded cliffs, the drowned trees, the glass, None of it was written to be read. It is just what stayed, the accidental residue of enormous weather. And yet a species that lives 80 years walked into this archive with hammers and reactors and trucks that shake the road and got most of it right. The dates, the depths, the tempo, the odds. Well enough to check the pressure of a sleeping volcano the way a nurse checks a pulse. Well enough to take the one scenario that frightens it most and follow it calmly to the end. And find on the far side not doom, but lupines, and a valley people travel to love. Somewhere in that work, without anyone announcing it, the fear changed state. What began as the biggest threat on the continent became a patient in long, deep, monitored sleep, and became, if we are honest, a kind of companion. Every generation before ours lay down at night on this same restless ground and knew nothing. We are the first who get to know, and what we know tonight is that it is resting. There is one more thing the record does, and it does it without being asked. It resizes the nights. The worries a person carries to bed are real, and nothing here makes them smaller in their own world. But they are worries built to a human width, hours and weeks across, and it genuinely helps to set them for a moment against a floor that takes 600,000 years to move. Not to be diminished by the comparison, nothing in this story diminishes us. We are, as far as anyone can tell, the only part of it that ever understood any of it. Rather to be held by the comparison, the way a small sound is held inside a large room and becomes strangely easier to hear. The ground under this continent has absorbed the worst it can do to itself 3 times over and come back green 3 times over, without hurry and without complaint. And it is very hard to sit with that fact for this long and keep believing that everything depends on tomorrow morning. Almost nothing does. The ground goes on. And tonight, on the best evidence a species has ever gathered about anything, it is going nowhere at all. So let the day we imagined go. It served its purpose. It made us walk the whole record, and the record, walked end to end, is calm. The plateau is dark now, and enormous and quiet. The instruments are awake in their small shelters, drawing their flat, patient lines. Old Faithful goes up on schedule, silver in the starlight, for no audience at all, and settles back. Out in the lake, the water leans imperceptibly south, resting on the slow roof. The drowned trees stand still in the shallows. They have stood there a long time. Far to the east, under the grass of Nebraska, the herd lies where it has lain for 12 million years, calves beside the cows, the ash packed close around them like bedding. In a creek bank in Kansas, the silver band waits in the dark. It has outlasted the post office that named it. It will outlast the road. 4 kilometers under the boardwalks, the crystal cap holds. The gas rises through it in fine, unhurried threads, as it did last night, as it will tomorrow night. Nothing is gathering, nothing is due. And in a museum drawer in Ohio and scattered through the soil of the park's North Hills, the black glass keeps its edge in the dark, 180,000 years old, carried by hand across half a world by people who thought it worth the walk. The ground that made it has been asleep since before their oldest stories, and it is sleeping still, and it is in no hurry to finish. Neither are we. Put the flake down gently. Rest now. Good night.